Joy, would you mind hitting the video processor button or video processor display? Is that going stage center and lectern 2? Could you try switching that? Joy, would you mind trying to switch that to lectern 1 from lectern 2?
Share screen. iPad via cable. Share.
Cool, thank you. It's okay. We turn the speakers off in here, but you should still see it. Can you confirm that on the record deck you're seeing the green lights when I talk? It should be lighting up maybe 2 or 3 lights high, something like that. Okay, cool. Thank you.
Sorry. Okay, so now this microphone is on, but is it working now? Is it working? Is it working? Hello? Hello? Okay. Okay, so just, sorry folks, we're just making stuff work. So what I was saying is this n over e to the n cancels one of these, and this n over e to the n cancels the other one. And so, after all of that, what remains? In the numerator, all that remains is 2 to the 2n. And in the denominator, we have this square root of pi over here. It's the square root of pi here. We have the square root of n. And that's it. So this tells us that 2n choose n, which if you remember, is the number of ways to put n ones in 2n spots, or all the binary strings of length 2n that have exactly 1/2 ones. That's basically 2 to the 2n divided by square root of n pi, which is to say it's exponentially the same size as 2 to the 2n. It's just 1 over square root of that in order. And this lets us understand that since this is true, we know that the nth Catalan number is approximately equal to 2 to the 2n divided by n plus 1 times square root of n, and then we have this square root of pi term in the denominator, which says that this is approximately equal to order 2 to the 2n divided by n to the 3/2. So this is an example of how we can use Stirling's approximation to understand how big a particular count is. Okay, so now I want to, again, try to see if the system is working properly, and I'll pause for questions. Do we have any questions? So just to make... Oh, I want to see if I can answer a question verbally. So can you have a question play out loud? So, okay, the question that was asked by text was, how did the second square root of 2 pi get canceled out? And the answer is it didn't. One of them, the 2 got canceled by the 2, but the 2 and the square root of 2n, but the pi remained. So the pi survived to the very end. Here it is. So I want to try someone asking a question out loud. So can we see if this works? Someone volunteer to ask a question. Okay, so call on someone who raised their hand. Okay, can someone please raise your hand and ask a question? Okay, Aiden Tan, it says, raised their hand. Yeah, allowed to talk?
Hi, can you hear me?
Yes, we can hear you.
Hello?
We can hear you.
Hi. How does the big O notation factor into anything? How did you get that?
So the big O notation is a notation which just says, I want to look at the dominant term. I want to look at roughly how this behaves. So here, the dominant term is that we get well, actually, you're right. The dominant term here is that we get 2 to the 2n, and then the denominator is behaving like n to the 3/2. So the denominator also has an n to the 1/2 in it, but the n to the 1/2 gets swamped by n to the 3/2 when n gets large. So when n is big, this whole expression, the nth Catalan number, will behave like 2 to the 2n divided by n to the 3/2. Of course, it'll have a constant offset, which is this square root of pi. So if you want, you can also think of that as being in here. But this is saying that up to constant factors, this is how it's behaving. Okay, good. So what I want to do next is to move on to the next topic that I would like to talk about, which is countability and computability. So Stirling's approximation, you'll get practice doing proofs with on the homework, and then we'll use it as needed to understand how big things are. In probability, this becomes pretty important. Preview of important things. This square root here and this pi, this is related to things in probability called the central limit theorem and so on. But you'll see all that as the course continues. So what I want to start now into is the idea of countability. And in countability, what we want to understand is how do we understand how to count sets that might be infinite in size, when sets are potentially infinitely large. So to understand how to do this, we have to kind of understand more carefully the zeroth rule of counting. So if you remember, the zeroth rule of counting says that if I have two sets, A and B, that their size is equal if and only if there exists a bijection H that goes from A to B. Now, what does bijection mean? Remember, this is two properties. This is one-to-one and onto. One-to-one means that this is also called an injection. And it means that no two elements of A map to the same element of B. And onto means that it's surjective, another word for this. Now, personally, injective and surjective confuse me like stalactite and stalagmite, so I have to always remember which one is which by looking it up. But one-to-one, onto are easier to remember for me. Surjective means that all elements of B have a preimage in A. There's something in A that maps to them. So there's a nice picture in the notes on the second page, which kind of shows you, illustrates what this looks like. But these are pretty intuitive concepts. So this is saying that two sets are the same size if you can have a one-to-one map that covers everything in the second set from something in the first set. And if that's true, then it has to be that they're in one-to-one correspondence to the same size. This is almost a definition of same size. So if this is the definition of same size, what's the definition of less than? Okay, so when I want to say that a particular set A has a size which is less than the size of B, how can I establish this? Well, this is true if and only if there exists a one-to-one map F from A to B. So why is that? It's because B is big enough to have a one-to-one mapping of A. There might be additional things in B left over, which is why we say the size of A is less than equal to the size of B. So these are basic facts that are very, very familiar from the point of view of how we think about counting things for finite sets. But we also want to say the same things hold for infinite sets. So what is the relationship between less than equal to and equality? So there's a very natural relationship that we want to establish. And the natural relationship we want to establish is that if the size of A is less than equal to the size of B, and the size of B is less than equal to the size of A, then the two sizes are equal. Okay. For finite sets, this is something you take completely for granted, but we also want to establish this in general for infinite sets, and this theorem actually has a name. This is called the Cantor-Schroeder-Bernstein theorem. And we walk you through a proof of this in the homework so you can understand why this is true. And what it's saying is basically if you have a one-to-one map from A to B and you have a one-to-one map from B to A, then in fact there must exist some bijection between A and B. And for this, we want to have a proof that doesn't rely on finiteness in any way, so that we can apply it for infinite sets. It's very natural. It should be true. So why am I focused on the idea of infinite sets? The reason is that infinite sets can behave in sometimes strange ways. So the classic example, not in the notes, that's used to illustrate this is this kind of image of something that is sometimes called Hilbert's Hotel, or I like to call it the Hotel Infinity. So this is an illustration. So the idea is there's a hotel, and the Hotel Infinity has an infinite number of rooms. In particular, it has rooms with numbers that are natural. So any natural number, there's a room. So there's a room 0, there's a room 1, there's a room 2, and so on. So the story goes like this to help you understand the idea of how infinite sets behave. For infinite sets, you can think of it this way. So we have the Hotel Infinity, and the Hotel Infinity is full. So they put up a sign saying no vacancies. So suppose full. Then a guest shows up. So the person says, please, can I have a room? And the hotel says, sorry, we're full. Every single one of our rooms has somebody in it. There's no vacant rooms. And the guest says, please, they're quarantining this infinite space, and I really need a place to stay. So the hotel, can you please move people around and make room for me? So the hotel says this. The hotel gets on the intercom, talks to every room simultaneously, and tells everyone, sorry guests, please move to the room whose number is 1 bigger than your room number. So someone arrived. Guests are told, move to room X plus 1. If they're in room X, move to room X plus 1. So all the guests do this. They move to the next room. And at that point, room 0 is vacant. Because the person in room 0 moved to room 1. The person in room 1 moved to room 2, and so on. So everyone moved. They all settled in to their new room. They moved in parallel. And then, room 0 was vacant, and new person got that room. So this story is used to illustrate the idea that for infinite sets, you can have interesting behavior, like infinity plus 1 is infinity. Okay, so any questions about this example? I want to make sure that I can answer it. Does anyone have a question? Yeah, I see someone raise their hand. Let's call on them.
Aren't some infinities bigger than others?
Yes. So the note talks about how the question is, are some infinities bigger than others? So that's something that we're going to get to. So actually, in ancient times, people wondered about this question, are some infinities bigger than others? And these kind of examples that you can take infinity and add 1 to it and get the same infinity, said that if there are any infinities that are bigger than others, they can't be obtained by doing these simple operations like adding 1. So we'll continue with this story, and you'll see how we can get to this. But the realization that fundamentally some infinities are bigger than others, and you can prove this rigorously, was a major intellectual accomplishment that we're building up towards. So we have this idea that one person arrived. So now the question becomes, what if an infinite number of people arrived? So think of it this way. This is a world that has infinities in it. And in this infinite hotel, an infinite baseball team arrived. So infinite baseball has players that wear jerseys, and there's a player for every natural number. The hotel says, they come in, they say, do you have an infinite number of rooms for us? And the hotel says, sorry, we're full. And the hotel, again, the team begs and says, please, we're here. We need to have rooms for all of our players. Can you please make room? So again, for this case, the hotel comes up with a smart idea. They say, guests are told, move to room 2X. So everyone looks at their room number. They move to the room whose number is double their original number. At this point, all odd numbered rooms are vacant. And then the hotel says, player I, go to room 2I plus 1. So with this example, we see how there's a rigorous sense in which infinity plus infinity is also infinity, or alternatively, 2 times infinity is infinity. So this example illustrates these are not different kinds of infinity. This is the same hotel. There's actually room for everybody in this hotel, even after 2 infinite groups have showed up effectively. So the story continues. And so this is basically what I'm doing now is a hotel version of the thing that's in the notes when it talks about cardinality, except I'm just going to tell you the classic story that people use for this. So suppose that now the infinite baseball league arrives. Now, the infinite baseball league has an infinite number of teams. With an infinite number of players each. Okay? So the idea is that every player has 2 coordinates associated with it. K, the team, comma I, player number. Oops. I don't know what happened there. So now the question is, what can we do? Can we accommodate the entire infinite baseball league? So if you notice, in this case, we can definitely free up an infinite number of rooms. We can again repeat to guests, hey, please move to the room numbered 2x. And now we'll have an infinite number of rooms vacant. But now we have to tell all of these players where they go. So the question is, we can't just say, okay, now we'll deal with the first team. The first team goes into all of the odd-numbered spaces. And then we say, again, repeat the process. Everyone moves to a doubled room, and then take the second team. The reason we can't do this is because the infinite baseball league doesn't want to wait around forever. They're willing to have infinite numbers, but not willing to wait forever. We need to be able to say one thing, a finite instruction that will actually get all of these players into a room. So if we can do that, that will show that actually, even though the infinite baseball league has an infinite number of teams with an infinite number of players in them, so this is effectively, we're trying to look at infinity times infinity, we can still fit them in the same infinite size, in the same infinite hotel. Okay, so do people understand the setup? So in the notes, this is very closely related to the setup for rational numbers, right? The question of how many rational numbers are there? Because all rational numbers are expressed as a pair of numbers, a numerator and a denominator, where both of which are, integers, or you can think of them as both natural numbers and you have a sign bit. So this is an interesting thing to do. In the notes, the solution for the rationals is done using a geometric picture of a spiral. I thought here I would try to give you an example that gives an explicit formula for what's going on. So does everyone understand the setup? I want to make sure that the setup is clear. I think there's a question. Can we call on them? Yeah. Question? You have a? Can we? I think you have to unmute them. So if you have a question, you need to unmute yourself before you can ask it, or we have to unmute you. I don't know how it works. Okay, so pick somebody else.
So my question is, I just want to clarify. So with the Infinite Baseball League, we're just assuming that all players are part of the same team, or because I'm a little bit confused about the KI setup.
Okay, so great question. The question here is, how many players have shown up? The idea is the entire Infinite Baseball League showed up. So there's teams. K equals 0, K equals 1, K equals 2, K equals 3, K equals 4, and so on. And there's also every single team has within it players. Player 0, player 1, player 2. So every player you can think of, it has their team name, which is a number on their jersey, and has a second number, which is the player number on their jersey. So these are infinite, substantial sized players that can hold these really giant natural numbers on them. And we want to assign every single distinct player their own room. So it's not that we can put the players from different teams into the same room because they'll fight with each other, and we won't put players from the same team into the same room either because they will also fight with each other because they just finished playing and they're tired and they want to rest. So you have to put all of these infinite number of teams as infinite players. All of them have to fit in the hotel. So is there another question about the setup? Maybe I can help illustrate the setup. So if you want to think about it, you can think about all these players as being on this grid. So we have teams on this side. So there's team 0, 1, 2, 3, 4, 5, 6, and so on. And there's players up here. Player 0, 1, 2, 3, 4, 5, 6, 7, and so on. And every one of these boxes here contains a player. So there's a player inside all of these boxes. Okay, so all these are little people. Okay, so we have all these people sitting inside of this grid. So we have an infinite grid, infinite two-dimensional grid filled with players, and you have to assign each of them a room. Is the setup clear? Any questions on the setup? Okay, good. So what I want to do is I want to kind of tell you how can you think about it? How can we kind of put everyone a number? So it turns out in this case, there's a pretty natural way to do it, and that is you want to take all of these players and come up with cohorts that combine players from different teams and then assign each of the players in each cohort into their own room. So a visual picture of this is we'll create a 0th cohort, which is this, a first cohort, which is this, a third cohort, which is this, a fourth cohort, that is this, and so on. So we'll take these cross-hatch things through this picture, and we'll assign them to cohorts. So maybe I'll make a table here. if you look at the cohort, there's a 0th cohort, which is this one. The 0th cohort has one player in it. Which player is it? It is the one whose k plus I equals 0. All the players whose k plus I equals 0, who add together the number on their team and their number for them, and get 0, they're in cohort 0. So there's exactly one player who satisfies this. 0 teams, 0th player. And so the number of players who have come before this is 0, because he's the first one. Then there's the first cohort, which has 2 players in it. This is everyone whose k plus I equals 1. And there was one player who came before. There's a second cohort, which has 3 people in it. K plus I equals 2. And there were 2 plus 1 equals 3 people who came before. Similarly, there's a third cohort, which has 4 players in it. And there was 1 plus 2 plus 1 plus 3. Sorry, so you have 1 and 1 plus 2 plus 3. So let me erase this mess that I made here. 1 plus 2 plus 3. So this 2 is this 2. This 1 is this 1. This 3 is this 3. This 1 plus 2 is this. 1 plus 2 plus 3, which is 6. So does everyone understand what's happening here? I'm going to keep track of how many players are in each cohort, and I want to basically assign them rooms in order. So first I'll put the players in cohort 0 into a room, then I'll put players in cohort 1 into a room, players in cohort 2, and I want to see, can I come up with a single formula that will allow me to figure out a unique number for every player using k and I. So there's many, many ways of doing this. This is one approach that I'm doing. You can come up with plenty of other approaches. So do people understand what I'm trying to do? My goal is to assign, assign player k comma I a room. If I can assign player k comma I a room, then I'm good. So if I have all the odd rooms free, I need to assign player k plus I a room. So it's a good exercise. So maybe I will mark this as an exercise. Show that 2 times show that this expression works. Okay? So what I've done is I've made an expression involving k and I. Oh, this is an I, not a j. That what it does is it says, basically, k plus I squared plus k plus I over 2, that is the number of people who've come before. And then every player has a unique column associated with this cohort. So let's look at the 5th cohort. So they go in order into rooms. And then, of course, I need to assign these to all the odd rooms, which is what I did here. So this way, I can assign every player in the Infinite Baseball League into a unique room. Okay, so working this out is basically involves showing that noticing that this is an arithmetic series, and just keeping track of everything. Okay, so I'm not going to work through the exercise, but I do want to take questions here so that people can make sure that everyone understands how this establishes that we've established effectively that infinity times infinity equals infinity. So, questions?
sorry, so I'm still a little bit confused. How are you supposed to know that this particular formula is the ideal? Is in the exercise is the ideal one to use? Is the ideal way to go? Is it because of the arithmetic series or just?
Sure. So when I say show that it works, what does that mean? Showing that it works means that this is 1-to-1 from natural numbers cross natural numbers, ki, so the teams, to natural numbers. Show that this is actually, it assigns every ki player into their own room, and no two different players end up in the same room. So that's the key thing you have to have, that all these infinite number of teams, these infinite players, all have to get their own room. So that's the basic thing. And in particular, second thing to check is that not just any naturals, but odd naturals, because we can only free up all the odd numbers by doing this trick of telling everyone to go to the doubled room. So this has to give everyone an odd number. It's pretty clear that going to odd numbers by construction, so this is not really that hard to do. And if you want to, you can also establish that this is, in some sense, the most elegantly efficient way to do it, because it actually lands everybody it fills all the odd rooms. Okay, it doesn't leave any spare. There's other approaches that are perhaps sometimes even easier to come up with that will land in odd numbers and won't fill all the odd numbers. But this one fills all the odd numbers. So the main thing about showing that it works is that it's 1-to-1 onto the odd numbers. Any other questions about this exercise and what we're trying to do? We're trying to show that infinite sets can have odd properties where things that you think make the infinite set bigger, like taking a two-dimensional version, gets bigger. Yeah, let's take another question. Question?
Hello?
Yeah.
Okay. I just had a question. So is it possible to imagine this? I guess if you took all the people who are currently in the hotel already, could you imagine that as a negative first team and then also map them that way?
So yeah, if you want to, you can think of everyone who's already in the hotel as being a -1 team and map them all. Yeah, that's the same thing. That would also work. So actually, yeah, so this is how all this can work out. So you can actually keep having fun with this, and the notes kind of jump immediately, but if you want to think about it, the next one, I won't do the next one, is the Infinite Olympics are in town. And the Infinite Olympics have Sport L, Team K, Player I. So now it's like a three-dimensional version of the same thing, right? That you have an infinite number of sports, each of which has an infinite number of teams, each of which has an infinite number of players. They all show up at your hotel, and your hotel is full, and they all want rooms. And it's pretty clear here that you can make this work, okay? So here, this is the counterpart of infinity cubed is also infinity. If the previous one here, infinity times infinity, this is infinity squared is infinity. So when people initially thought that there were many different kinds of infinities when in ancient times, they were frustrated by this sort of behavior. They kind of knew this sort of behavior could exist, and it felt that it was very hard to actually get to any kind of bigger infinity than the infinity of the naturals. Now, the reasons they wanted to have bigger infinities was usually for theological reasons and things like this, kind of numerology and things like that. But it was a real question of, where are these bigger infinities that are actually bigger? And for some time, what people believed is that actually there really was just one kind of infinity. There weren't the bigger infinities than the standard infinity of the countable infinity, the infinity of the natural numbers. And it was Cantor who showed that actually there are different infinities. So this is something that's called Cantor's diagonalization proof. And in a way, what it shows is, if you want to think of it very symbolically, what it shows is that 2 to the infinity is bigger than infinity. So this is like in quotes. So what did Cantor show? So what Cantor showed was he wanted to look at real numbers. From the interval, from the unit interval. So how many real numbers are there on the interval 0 to 1? And the answer is, so this is like, this interval, 0, 1. Every position on this interval corresponds to a different real number. The question is how, so, some x is here. So we're thinking about x that's in the interval 0, 1. How many such x's are there? How many such real numbers are there? And how do we count them? And how do we understand, whether there's more of them than the naturals or the same number as the naturals? Because these examples of the infinite Olympics and so on showed us that just because you say there's it feels like there's a lot more, definitely feels like the infinite Olympics has more players in it than a single infinite team, it turns out that actually the infinite Olympics has the same number of total players as a single infinite team. So how do I know that the real numbers actually have more players? And so we basically, it's a proof by contradiction. Okay? What it says is, assume otherwise. Assume there exists a map F that is 1 to 1 and maps the interval 0, 1 into the naturals. So what this does is assigns a number to each real in 0, 1. So suppose that such a map existed. If such a map existed that was 1 to 1, it would show that the number of reals is less than or equal to the number of naturals. So what we want to do is to get a contradiction. And how do you get a contradiction? To get a contradiction, we want to show that, assuming the existence of this map, that actually we missed a number. Okay, that no such map can exist because we'll miss a number. So the way the proof works is as follows. It says, arrange the decimal expansion of the x, namely f of 0, f of 1. So let me correct this a little bit. I wrote this map backwards from what I want. I want to show that so let me write this. That is a bijection and maps the natural numbers to the set 0, 1. Assigns a number to every real. So yeah, sorry, I wrote this backwards. So I want to basically say that I have a number for every real number, and I have those numbers are unique, and which means I can also take all of the reals and I can arrange them in order. So I have these real numbers. I have the first real number in my ordering, f of 0, the second real number, f of 1, and so on, going off to infinity. And I'm going to look at their expansions. So I look at f of 0 equals 0 point f of 0, 0, f of 0, 1, f of 0, 2, f of 0, 3, and so on. And similarly, I have f of 1, which is 0 point f of 1, 0th digit, f of 1, first digit, f of 1, second digit, f of 1, third digit, and so on. And then I keep going. I write them all out in this grid. Okay, so I do this. I keep writing all the numbers out in this giant grid. And I want to claim, by saying that I have a bijection that maps the natural numbers to 0, 1, which means I can go back and forth between the real numbers and 0, 1, that I've put every single real number between 0 and 1 into this list. And I want to create a contradiction. So I want to show that this can't possibly work, that I must have missed a real number. So I want to find a real number. So I want to construct Q, which is a real number from 0 to 1. So it's going to be 0 point something. That's not in the list. So this is what we're trying to do. This is Cantor's diagonalization proof that actually the reals between 0 and 1 are a much bigger set than the naturals, so that no such map can actually exist. No bijection can exist between the naturals and this set. So to show this, we use a contradiction. We say, assume that such a map does exist. Once I have such a map, I arrange everything in order, and now I want to construct a Q that's not in the list. And so the trick is, we just look on the diagonal at this, 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 and so on, all the way down. And I make a Q out of all these numbers on the diagonal. So what I do is I say Q is 0 point, I take the first real number, and I do some operation to it, to the digit, to get a new digit. Then I take the second real number, and I take its second digit, and I do the same operation to it. Then I take the third real number, and I take its third digit, and I do some operation to it. So this operation changes that digit. Okay, so what is this bar operation? So I'm going to define 0 bar is 1. So if you write that in decimal, 0 bar is 1, 1 bar is 2, and so on, all the way up to 8 bar being 9, and then I'll make 9 bar equal to 1. This is for technical reasons. I don't want to wrap around to 0. I want to go to something different. So I'll go to 1. So if I do this operation, so what is Q? Right? Q is the sum I equals 0 to infinity of I equals 1 to infinity 2 to the minus I f I minus 1 bracket I minus 1 bar. Okay, so explicit expression. So this is the formula. Now, Q differs by construction from F I in the ith decimal place. Okay, this is how I built it. Cantor built this number q for contradiction in such a way that it would differ from any number in the list in a particular place. If you look at the ith number in the list, it differs in the ith decimal place, which means, yeah, so, sorry, yes, thank you very much for the correction. I am so used to working in binary, I forgot. Yeah, 10. Thank you very much. Yeah, because I'm doing decimal expansion. So if you look at this argument shows that you have this number and it's different from every single other number, which means that there is no j such that f of j equals q. So f can't exist. Okay, so what this proof does is it shows that there is no way to actually take all the real numbers from 0 to 1 and map them in a one-to-one way onto the natural numbers. There's simply not enough natural numbers to hold it all. So why did I call this saying 2 to the infinity is larger than infinity? Actually, you can think of this as actually what I actually showed was 10 to the infinity is greater than infinity. Because what's the 10 to the infinity? This is the binary expansion. Sorry, not binary, decimal expansion. So Cantor's proof was what showed the world rigorously that there were different kinds of infinity. And a bit of a comment on this, maybe a slightly sad comment, many people believe that the shock of this proof in part helped drive Cantor insane. And a poor man died not well mentally. But it was an incredible contribution to the intellectual history of the world to realize this. Very, very simple, elegant argument that showed that actually there are different levels of infinity. And so actually this keeps going. There's like many, many infinite number of levels of infinity. So I'm going to stop here and ask for questions before moving on to the next topic. So any questions on the Cantor's diagonalization proof showing that there is no one-to-one onto mapping from the naturals to the reals between 0 and 1, and hence not to the reals generally? Questions? Anyone raise their hand?
So I want to ask a question about, like, for example, in Cantor's proof, you change the numbers that's along the diagonal line. But I want to ask, what if you change the direction? For example, you only change the first digit in each of the fj you created. Will that kind of operation create a new number that is not in this fj?
So if you're seeing that, why not look at these numbers and just change all of them?
Yeah.
If you looked at these numbers and changed all of them, that could very well be the second number, right? Because the second number, it doesn't intersect, right? This thing won't intersect with it won't necessarily cause a contradiction. The diagonal forces you to have differences in this way. Okay, so the diagonal was a very important part of this trick, was to use a diagonal. If you just use the vertical, it doesn't have to be the case. So, for example, you could very well choose to arrange the numbers in alternating first digit. So think of the binary case, okay, just for simplicity. Think of 0.1 something and then followed by a 0.0 something. And you keep alternating that. Well, if you do that, there's nothing to say that if you flip all of them, you'll just get perhaps even the second number itself. right? The 1 will get turned into a 0, the 0 will get turned into a 1, and it'll be 0.01010101, and that's nothing wrong. That could have very well have been the second number with no contradiction. It was very important for this proof that we actually indexed in different places throughout. Turned out to be important for the way that this proof was built. Because you have to show that you are actually different from the jth number. How are you different? Because you're different in the jth place from the jth number. Other questions? Yeah.
Yes. So my question was again about the setup. So I realized when we're doing the diagonal from f0 index to 0 and then f1 index to 1, it seems a little bit like like the row echelon form of a matrix. Would that have to so basically we're constructing cube based off of like whether or not like we're able to define a specific number that has a digit that a certain digit at a certain index that we can index into. There's more of a clarification.
So here, yeah, we're definitely using the fact that we can treat numbers as existing on a rectangular grid, infinite rectangular grid, and we want to look at the positions on this infinite rectangular grid and use them to construct a new number. So that's true. We are using the kind of grid kind of view. It's not really connected to any matrix operations per se, because we're not doing any operations on these. We're just arranging them. We're saying that, so think about what's going on here. We want to prove that no such f exists. To show that no such f exists, we assume that it did exist, and you want to get a contradiction. So you can't actually construct this grid because there is no such thing. But you said if we had such a thing, we could construct this grid. But then this grid wouldn't be complete because you take the diagonal and you flip everything on the diagonal, and that's not anywhere in your grid. So it's like, again, it's the usual proof by contradiction thing. We make an assumption for something we want to show does not exist, and then we prove why it's inconsistent, right? Why it has a fundamental inconsistency in it, and blow up that world. So this grid doesn't actually exist. It's just we're saying it can't possibly exist, which is different. Okay, so this is Cantor's diagonalization argument, and after Cantor's diagonalization argument came out, it really was very inspiring to a lot of people. And one of the things that happened was that this idea of something that seemed like it maybe should be natural, they should be able to find a mapping, but you can't in this case. And you can do that by creating kind of a contradiction in this particular way. It was interesting because in a way what we did was we referred to a number, we pretend there was this list, and then we asked for these kind of echoed positions, right? You see this, 0, 0, 1, 1, 2, 2. You asked the ith number for its ith place. Okay, there's this kind of interesting thing. You ask the ith number for the ith place within it. So this is about numbers that have like internal structure. You said, let me query you inside. And we used that to create a contradiction. So this is the idea, this inspired people to start thinking more deeply about the idea of self-reference, which is, can things refer to themselves? And this is also important for other reasons in mathematical set theory and so on. People wanted to know what you're allowed to do, what you're not allowed to do. And a whole bunch of things came together historically in a way that culminated in, I think, really something which we believe is one of the intellectual landmarks of, I think arguably it's an intellectual landmark of the last, 3,000 years kind of level of accomplishment. Like this is an accomplishment that will, 5,000 years from now, people will remember that there was a time when humans figured this out. And it was an important time philosophically. It's kind of like the theory of the atom, the idea that things can be divided into particles, and indivisible things. The same way, the idea of computability is, I think, the easiest way to grasp it. Because now that we have access to computers. When people came up with these arguments, they didn't have computers. It was really amazing. Because to come up with the idea of computability without computers was really quite something. But now we have computers, so it's easier to understand. So the idea of computability is to say that it turns out there are very natural properties of programs, and by extension about statements in logic. They're very natural statements that you can't figure out if they're true or not. And for programs, there's very natural properties of programs that you can't check by a program. And so the way that this is usually talked about, and most naturally, is called the halting problem. But before I talk about the halting problem, I want to give you an idea for why there is a deep connection between the idea of the halting problem and this idea that there's infinitely many real numbers, and there's so many of them that there aren't that they can't be put into one-to-one correspondence with the natural numbers. So if you think about it, the programs we want to think about are finite programs. What do I mean by finite program? I mean a program that can be written as some finite string in some programming language. So if a program, what this says is that programs are like natural numbers. And in a way, we can make this stronger. We can get rid of the like. We can say programs are natural numbers. What do I mean by that? What I mean is we take a programming language, whatever it is, we take any natural number we want, write it out in binary, convert that to a text file explicitly, interpret it as a text file, and call that a program. If we do that, every single program is actually some natural number. Now, most natural numbers are not very interesting programs. They just syntax error instantly. Right? They're just syntax error. They're malformed. But that's fine. If we think about an interpreter, a program that is a syntax error is still a valid program. It just happens to immediately halt with the message syntax error. So this way, we can think of programs as being natural numbers. Once you think about programs as being natural numbers, there's an interesting thing. If there's a property that you have that you associate with programs, a property that you associate with programs that can be, say, true or false, that's like an infinite binary string. So programs are natural numbers, but properties So what do I mean by that? I look at 0 point P1, P2, P3, and so on. What this means is Pi equals 1 if program I has this property. Okay? And Pi equals 0 if program I does not have this property. So, although programs are natural numbers, properties of programs are like real numbers. And they're like real numbers between 0 and 1. Okay? So, the fact that although programs are natural numbers, but properties of programs are like real numbers, tells you already from Cantor's diagonalization that there's going to be some properties of real number, of programs, that can't be checked by a program. Okay? So, let's just let me write that down. Because the size of the set 0, 1 is much bigger than the size of the natural numbers by Cantor, there are properties, perhaps abstract, of programs that can't be checked by a program. Okay, why do we know this is true? Because if you had a program that could check this property, that program could emit that real number out as a string. It could just go through a loop where it says, let me check program 1. Does it have the property? I'll output 0 or 1. Let me check program 2. Does it have the property? Program 3, program 4, and so on. If you had a program that could check this property, you could emit this real number. But you know that they're real numbers that you can't possibly emit because you only have a natural number of programs, and you have an uncountable number of potential properties. So the fact that there's a property of programs that you can't check by a program is already clear in spirit from Cantor's proof. The interesting thing in the halting problem is whether or not any of those properties are interesting properties or not. And what Turing showed, and actually this is like credit to Turing, to Gödel, kind of the large spirit of work here, is, let me write down Turing's name, was he showed that, in particular, the property does this program halt or not? Does it go into an infinite loop or some kind of other infinitely long computation, or does it actually terminate at some point? This property is uncomputable. So that's what the halting problem says. It says that the most basic kind of thing you want to check in an automated debugger, give me a program, tell me, is this thing going to at least not loop forever? That most basic property, no computer program can check. Meaning what? Can it check it? Yes, it can check it, but it can't always be right. It can't give a definitive check. It can say, yes, this program will terminate. No, this program will not terminate. But it also has to leave open the possibility of saying, I don't know. This is a program, I don't know if it's going to terminate or not. So how does this proof go? So to show that this kind of a program can't exist, you again follow a contradiction argument. So what you do is you say, suppose I have a program for contradiction. Assume we have a test. Okay, the test program we call test halt. It takes an argument p, another argument x. So you have a program, you feed it an input, and this says, yes, if program p halts on input x, and no, if program p runs forever on input x. So you assume that you had such a program. So when I say I have such a program, it means I have a computer program that takes two inputs, p and x, both of which are natural numbers. And if program p halts, including possibly by syntax error or crashing, I say yes. If it doesn't halt, I say no. So if you had such a program, which cannot exist, but we're going to assume it exists, then I could make the following program. In honor of Turing, we call it Turing, which takes one input, P. And what this program does, it uses test halt as a subroutine. It just says, if test halt, when run with program P, and input also program P, if this says yes, so if test halt says that program P given input P will actually terminate, then Turing will loop forever. I mean, so for example, Turing can just, this can go to the same thing, keep running the same check over and over again. Else, if test halt says that the program will not halt, if test halt says the program will loop forever, then halt. Just return 5 or something, doesn't matter. Stop. So this program Turing, if we had a program test halt, we can definitely write a program Turing. And the question becomes, what does Turing do? If I could construct this program, I can run this program feeding it itself as an input. If I do this, let's just watch what it does. I feed it to program Turing. So Turing of Turing just says, if test halt on Turing running on Turing says yes, so test halt says, if test halt says that Turing running on Turing will halt, then I loop forever. So if test halt says Turing will halt, it won't. If test halt says Turing will loop forever, it halts. Which means that Turing doesn't do what test halt says it does. So either test halt is wrong, or it can't exist. Either way, no computer program can check whether another computer program halts. Okay, so now I want to take questions on this thing, because this is an incredibly simple and elegant argument written out. It's very short, right? Like it's like it fit on one page, the entire argument. But what it established is that there are actually interesting properties of programs that no program can ever figure out in a definitive way. So I want to take questions here, and then we'll close lecture. Questions on this? Yeah, let's speak.
I'm just going to clarify. So when we're constructing the Turing, just out of curiosity, how are we supposed to know that if the test software produces a yes, then we're looping forever, and otherwise we're not looping. Basically, how are we supposed to know that the Turing function is supposed to do the opposite of test halt? Is that something like intuitively we're supposed to know already? Or?
Yes, the question is, so I'm giving you the construction. This is Turing's construction, so Turing constructed this way. But this construction is exactly the same as this construction. Right?
Okay.
It's exactly the same as this oppositeness construction here.
Okay.
Right? So the Turing function as a program is the same thing as Q was for a Cantor. It's a program that can't exist. that test halt can't check. So test halt claims to check everything, and Turing says, I'll show you. I will make a program, Turing, that test halt gets wrong. So the idea that test halt is wrong is the same as there's no J in this list.
Oh, right.
Right? So it's saying that this is too much to ask for. It's the same exact argument. So these are called diagonalization style arguments that say, they're proof by contradictions, that say something can't exist. And you assume it exists, and you show that you claim to be exhaustive, you claim to be able to do everything, but I will construct something using you that you can't do. In this case, test halt is used to construct Turing that test halt can't check. So, other question? Can someone raise their hand? Okay, so we have now hit the time. So I just want to make one last comment on this. So this material that showed that there are fundamental limits to what computers can do, actually the same argument applies, although a lot more work has to be done, to logic. And what Gödel did was to show that just like programs are natural numbers, you can actually take proofs and turn them into natural numbers too. And you can take propositions and turn them into natural numbers too. And then you can show that there are statements about the integers that have no proof. They're true, in a way, in that for the familiar integers you think of, they're going to be true, but there's no proof of the fact they're true. They just happen to have no counterexamples. And what that did was it showed that there's a distinction between provable and true. All things that are false are falsifiable. There's a counterexample. But things that are true, it turns out, can be true with no proof. And that fact about the natural numbers was something that still everyone has